So RSA is going to be one of the kind of very important crypto systems that we'll want to talk about. And really briefly, RSA also brings in this idea of public key or asymmetric cryptography. So this is something that I think I might have mentioned briefly before, but it underpins a lot of how we can actually practically use crypto today. So what public key means is that we have a sender and receiver, or two sides of the conversation really, and they use different keys. So with symmetric key, remember we had the same key. With asymmetric, we have different keys. And this is really the key, not to make fun there, this is really the most important part of it, is there's two separate keys. And the idea here is, let's say you're Alice and you want to get Bob to send you a message, right? So you can freely publish a public key, and so the public key performs one operation, in this case only encryption. So this public key can only perform encryption. The private key can perform decryption or encryption. But what this means is that because the public key cannot decrypt the message, Alice can give that public key to anyone. As soon as Bob encrypts the message with this public key, in theory, even Bob can't decrypt it. Of course, Bob knows what he sent. In most cases, that would be the idea. But someone else who has the public key can't see it. Only Alice can decrypt it with the public key. So this is really the most important part, is that we have two separate keys, a public key and a private key. So this is why it's also often called public key cryptography. Asymmetric or public key cryptography basically has the main pro, I mean there's a few other ones, but the most important part is it solves this key distribution problem, right? So we no longer have to worry about the security of our key in transit, because we have a key that only performs certain operations. There are a few cons. It's much slower. So if we look at encrypting, say like, a megabyte of data or something like that, it's much, like hundreds to thousands of times slower typically than symmetric crypto. It's also much larger, so the algorithms themselves in terms of code size, or if it's hardware in terms of area, are much larger. So this is both code size and area. Oops, let's make that vaguely. So when we say area, that's like how much, if you had a physical chip, how much of that physical chip is needed to actually, implement this algorithm. The other disadvantage, and we'll talk quickly about that, is that most classic or really current asymmetric algorithms are vulnerable to quantum computing. So there's upcoming methods that might be able to break asymmetric algorithms. They don't actually work as effectively on symmetric. Symmetric algorithms are not in threat by quantum computing, or not in serious threat, but asymmetric algorithms may be. Okay, so what's RSA in general? The background to RSA is created by the idea of this public-private crypto system introduction. So when it was first introduced in 1976, it wasn't fully, I don't want to say usable, but fully implemented. It was basically implemented as a way of doing a key exchange where both sides were able to generate a key without it being transmitted over the clear. But there was this open problem of what we call a one-way function. So a one-way function is easy to compute with known inputs, but very, very hard if you just have the output to reverse it. So if you have like a little block here, right? So this is one way, and we put in 7 and 115, right? It does something that equals, and I'm not going to make this a real one, right? It generates some output here. And the idea is that it's very easy to be given 7 and 115 and calculate 892, but it's very difficult if you only had 892 to know what the inputs were, to calculate the inputs. So this is what we call a hard problem, right? So it's hard, and when we say hard, we basically mean impossible, right? It's not theoretically impossible to do so. It's just so computationally costly, we can't effectively do it. Right, so there's lots of hard problems in life, like who are my real friends, what is God, and the important one to us is factoring integer multiples. So this is a hard problem, and by hard, again, we mean it can be computationally very, very difficult. Okay, so what do you mean when we say factoring? Basically, if we have integers that, if we have prime numbers, prime integers, and we multiply them together, we get some larger number. And if we're only given that larger number, it can be very hard to figure out what factors were used to generate it. So if we take two primes, for example, 7 and 11, if we multiply them together, we get 77, right? This is easy. So if you're given 77, you could basically brute force, all possible prime numbers to figure that out. This seems easy right now, but it gets complicated quickly if we have much larger numbers, right? So in cryptography, we'll often call these two numbers P and Q. So we'll have, and these are two primes. So these are primes. And this will be part of the key. And the idea is if we just give someone n, they won't be able to figure out what P and Q is. And the reason they can't is the numbers are going to be so large. So if we look at those numbers I had, like 7, right, is binary 111. That's 3 bits, right? 11, so the other number, remember we had 7 times 11. 11 is going to be 4 bits, right? Because we could write that out in 4 binary bits. So this is a 4-bit number. And so you can see these are pretty small numbers, right? If we look at a slightly larger number, even 80, right? So I just picked an arbitrary large number, is 17 bits long. And this is pretty common if you look at like your computer system, right? You have 8-bit, 16-bit, 32-bit, 64-bit. These would all be integers you would commonly use. RSA has sizes that are much, much bigger. So as an example, the RSA key size, each prime is about half of that because this is the n equals P times Q, right? So this is the n. So if it's 512-bit, right, P is about 256 and Q is about 256 bits. So what does that look like in practice, right? And RSA 512 is actually never used. 1024 is basically not used anymore either. We have some 2048, but it's not used as commonly. We go down to RSA 4000, or 2048, sorry, is used commonly. And we can go up to 4096. So to give you a feel, even RSA 1024, a key would look something like this. So this is just writing out a 1024-bit number, right? So these are huge, huge numbers. Normally these problems are called like big number problems or something like that. And so this is like big number math. And the reason I have this big number here is that you'll often see like big num libraries. So big num libraries deal with these big numbers because you can't just implement RSA normally by just throwing that into C or something like that. The numbers are too big. If you're using Python and stuff, and it can actually deal with pretty huge integers, you may need special libraries, but you can do a bit of experimenting if you want. So really briefly, we're not actually going to go into too much detail on how RSA works. This course isn't about cryptography itself. This course is just trying to show how it's used. So very briefly, if we're encrypting a message, we're calling our message M for now, right? So M is some number, and we'll talk about how we generate that. And we basically raise M to an exponent E. And this exponent is part of the public key. So this is the known public key or public exponent. So the public key actually consists of a few numbers, not just E, but this is just part of it. So the other part is actually this N number, right? Remember N was equal to P times Q, and it's also part of the public key. So those two together can make up the public key that we can just freely share. So someone can encrypt a message by performing this operation to get a ciphertext, And the important thing is it's done in this modulus n, where n is, again, that big number. So we take this exponent, our message, to the exponent of the public key. We get our ciphertext, so this is the cipher that we could freely send to someone. So for someone to decrypt it, and again, these are just numbers, they can basically raise it to the private. So this is the private exponent. And what you can basically think of is a lot of this stuff has the effect of undoing the operation that was done with the encryption. So we have a carefully chosen, and it's basically calculated when we're generating the keys, a private exponent. And this is all related to the selection of n, right? So the selection of these two p and q integers works out in such a way that we pick e and d, so that the raising the ciphertext to d effectively can remove the effect of the encryption in this modulus n operation that we're performing. So this is at a very, very high level how RSA works. So the important part is really that it involves taking your message to some exponent, either the public key or private key exponent, depending if you're doing encryption or decryption on a plaintext or ciphertext. So what is m, right? So we have this very vague idea that n is some number, right? So m should be your message, but you would normally have like a message that's like a text string or a file or whatever you're trying to encrypt. Right? We can't raise a sentence to an exponent. You can't just sub that in directly. So we use a scheme, and we'll call it a padding scheme. It actually does a few other things too that basically converts this to an integer. So you could imagine if I was trying to say hello, and we just have to agree on it, right? So let's say I was trying to encrypt hello. We could just say, well, I'm just going to use whatever letter of the alphabet this is, right? So whatever this would be, I'm going to just guess here now. Right, so if we just substituted wherever these are in the alphabet, I should have looked this up ahead of time. Let's say that's halfway through. And we could just make a number out of that, and we would maybe pad it so that it's in agreement, right? So that's one way of generating a number. Obviously, what you really do is you could use like ASCII table or something like that to generate such a number. But we just have a scheme, and we just have to agree on that scheme that can convert the message into an integer. The padding scheme also, it does a little more than that. So the other important thing is there will be some attacks, and we'll talk really briefly about RSA attacks that are possible on, if we incorrectly choose a message basis. So the padding scheme basically ensures that no matter what the user tries to encrypt, it doesn't end up with a weak attackable output. Yeah, so that's a real high-level, fast summary of RSA. The important takeaways is we use asymmetric or public-private keys, and this is an important part of asymmetric cryptography. The security of all of these is based on the integer factorization problem, right? So if we have two prime numbers, n equals p times q, and I pick p and q as primes, right? And so we choose primes so that there's only one solution to this problem. And I just give you n, so if you have n, it's very hard, impossible basically, for you to figure out which two primes I chose. It also relies on a padding scheme, so the encryption itself isn't quite as useful as just like when we discussed AES and things like that. You need a little bit of a framework around it to actually use it in practice. And this how you use it is called the padding scheme. And so there's a few available ones. The most popular would be used by most systems out there. But, if you have an RSA block, you need to add a little bit around it when you go to use it. Yeah, so we'll next look briefly at attacks on RSA, and you'll see what sort of level is actually needed to break this with current computing resources.